The broadcast is now starting. All attendees are in listen-only mode.
Good morning, everyone, and welcome to our webinar today. And the topic is testing the ground circuit. Before we dive into our material, let's meet our team. I'm your host. In fact, I'm your presenter, Sayed, one of the applications leader. We also have Anthony helping us today as a panelist. He will be assisting you with any questions that you may put up on the chat line. And lastly, we have Brittany, as always, the organizer and running the show here. So a few webinar notes. Again, the Q&A utility is always available for any questions concerning the material being presented. You can also find a recording of this webinar on our website, probably in a matter of a day or two. And then if you have any questions regarding any connection issues, video or audio issues, please feel free to address those to Brittany at the following email address, brittany.soha@iconixusa.com, and also use our chat line to contact Brittany if you are having any trouble with the presentation and if you have any other questions. So, okay. Here is what we're going to be trying to cover. Ground. We're going to try and understand what is ground, and then what type of products incorporate a ground circuit, what is it really meant for, and then why is there a need to test the ground, and why is it important to test the ground, and what are some of the requirements as per the test standards. How do they want us to test the ground circuits of our products, and the pass-fail criteria. And in doing so, we will also touch up a little bit upon the ground continuity test, which is similar to the ground bond test, but gives us a slightly different result and understanding of the product. So first thing we want to understand and learn is what is a ground? What is ground meant for? What are its different uses? So first of all, think of ground as a reference point for an electrical circuit. As you know, if you think about in terms of voltage always has to be referenced to between 2 points. There's a high point and there's a low point. And sometimes, ground is used as a internal reference point. It's also used as a line of defense against electric shocks, which we will learn a little bit more about. And in some cases, some definitions describe it as a common return path for electrical current. So, in other words, ground or earth can have numerous different functions and meanings, but the main purpose of having or incorporating a ground circuit in any electrical product is to reduce the risk of electrical shock, as well as protect the equipment itself from being damaged. And the electrical symbol for ground is the symbol on the left side of the slide, which is very commonly used in drawings and schematics. So in power distribution, in most cases, the power that we get from the utility, we get a grounded neutral type of output or power, which means that the neutral side of our wall outlet is grounded, and again for the very reason of safety and protection. And in case a ground fails, the ground is bad, a lot of things can happen. First of all, there's no path. If a ground is not continuous, or if it's not there, there's no path for any fault currents to flow, so or flow back to the earth, which can result in damaging the equipment as well as people getting shocked. So from the utility, our power that we get is grounded on the neutral side of the line. So again, talking about the different functions of ground, there's the service ground, and then there's the equipment ground. Service ground meaning the ground that we, how the output is grounded on the wall outlets, and its main purpose is to protect equipment, tools, and insulation. And then for the equipment ground, like for a product that has a ground circuit or a ground pin, that ground serves as a barrier from electrical shock. It protects the operator, and it routes any fault currents safely through the grounding circuit back to the earth ground, instead of that fault current taking the path of a human who's in contact with that product. So based on all this, I mean, we can imagine how important a ground circuit is. And I know there are devices that are not grounded, but they're then the lack of ground is made up by reinforced insulation or double insulation, and making sure that the product is still safe to use or operate. And then this also gives us an idea of why is it important to test the ground circuit of a product and make sure that the ground is continuous, as well as capable of dealing with any fault currents and routing it back to earth ground. So here's a quick look at the two different types of or two different classes of products that we commonly run into. I'm sure there are other types out there as well, but the most common ones are the class 1 and the class 2 products. The big difference between the two is one class of products has a ground, which is class 1, and class 2 products, they don't have a ground circuit. So for class 1 products, they normally terminate in the US and almost everywhere around the world. If it's a single phase line neutral grounded product or an outlet, you'll see that there's a third pin, which is a ground pin, and it's normally connected to the product's chassis, meaning that, and it may be connected to different points on the chassis, different metallic points or conductive contacts on the chassis, to ensure that if there's any current, fault current that's going to flow on those conductive points, those points are grounded, and all that current will be routed through the ground back to the earth ground. Then we have the class 2 products, which normally terminate in a 2-prong line cord. So there's no ground. The third prong, which is the ground, is missing. This is made up by using a double insulated or dual layer of insulation, or double insulating the product. Now, as we know from some of our past webinars, that there's ground and then there's insulation. Both of these are considered as barriers from for electric shock. So for a class 2 product, since there is no ground, the insulation is double insulated. The product is double insulated, and that's the only safety barrier that you have. So again, class 1 products provide electrical protection by employing a basic insulation and a grounded chassis. Class 2 products employ a double layer of insulation, or dual or reinforced insulation, so a grounded chassis is not necessary. Let's look at some of the definitions per the NEC, which is the National Electrical Code. And obviously this is more applicable to the US, but I'm sure there are similar regulatory agencies around the world, or the part of the world that you guys are in, which are regulating or describing and defining what is a good ground. So per NFPA 70, a good ground should protect people and property from electrical hazards. Okay, that's basically a very basic definition of ground. Then we have another NEC standard that says any exposed non-current carrying metal parts of cord and plug connected equipment which may become energized shall be grounded. So this one's basically requiring the use of a ground circuit in products which may become energized and which may have non-current carrying metal parts. So basically any exposed metal conductors which may be non-current carrying but can become energized must be grounded. And then we have another example from NEC 250-51, which is describing a ground should be permanent and continuous. It should have the capacity to conduct any fault currents that may be imposed upon it due to any internal faults in a device. And lastly, and this is the most important one, is it should be low enough impedance to limit voltage to ground. So you want to make sure that when you design a product and which incorporates a ground, a safety ground, that ground must be low enough impedance, much lower than the impedance of human body, so that current takes the path of that low impedance circuit rather than flowing through a human being who comes in contact with the device. So the NFPA, the National Fire Protection Agency, again, this is more geared towards the US market, stipulates that the NEC, which is adopted on all 50 US states, the NEC gives requirements for grounding products and installations and defines a good ground. So again, I'm sure there are agencies describing a good ground in different parts of the world, which should be pretty similar to these requirements. And again, this is a great resource. The NEC code in the US is a great resource for learning more about ground and safety of products in general. So the other thing is, I forgot to mention, is that ground also protects against fires, because anytime there's a short circuit, high amounts of current can flow in a breaker, and if it's got a good ground, it will take care of all that fault current and route it safely back to earth ground, rather than it resulting in heating up the breaker and resulting in a fire. So that leads us to the two types of tests that are mostly called out for or required by most of the standards. The first one is a continuity test, the ground continuity test, and the second one is a ground bond test. Now both these tests are either used on the same product. You could start with a ground bond test and also perform a ground continuity test, or it could just be a ground bond test, or just simply a continuity test. So the purpose of these tests, of the ground bond and the ground continuity tests, are to check the ground connection on a product or a system and ensure, it's a way to ensure that the ground circuit of a product that you're testing is, number one, continuous, and number two, capable of handling a high amount of currents for a given amount of time without breaking or without melting or heating up too much. So that's the purpose of the test, and the method of running these tests. And again, we'll go into more details on how exactly the test is performed. But the way it's, just to briefly cover it right here, a small signal is applied. For a continuity test, a very small pulse or signal is applied from point A to point B. And if the signal makes it from point A to point B, we know that that path is continuous. That's all the continuity test is telling us, is there's a continuous ground. And for a ground bond test, we were basically testing the same ground circuit, but in this case, instead of a small pulse, we're applying a high current, a high amperage. It could be anywhere from 10 amps, 15, 20, 30, 40. We've seen applications where 60 amps of current is being used to check for check a grounding path or any other path in that ground bond test is used for checking resistances or impedances of any electrical path. So the main purpose is to test the ground, but there are other uses of the ground bond test as well. And the result of the test should determine, or at least what we're looking for, is that the ground is continuous, permanent, and capable of dealing with any high currents, capacity to conduct fault currents, and should be low enough impedance to limit voltage to ground. So these two, the ground continuity and the ground bond tests, are used to prove and verify that there is a low impedance path to ground for electrical products and systems. And also in doing so, we're ensuring that we have proper grounding available. So that leads us to our first question, which is a quiz question here. And the question is, which of the following best represents the result of a ground bond test? The poll is open, so I encourage you to please participate in this. And we'll take a brief pause here.
Hey Syed, we had 17% of attendees say 1 kVA, 0% said 1 mega ohm, and 83% said 1 milliohm, and then 0% said the last one.
All right, thank you, Brittany. Okay, well, thank you for taking part in this quiz question, and the answers are, obvious. The 1 milliohm is the most, is the closest you can get to a ground bond, result, because what we're measuring is the impedance of a ground circuit, and we want it to be very low. So normally, it's usually measured in the milliohms. Okay, so then that leads us to our circuit for a ground bond test. And what we're going to do here is take a look at the different connection points. On the left side, what we're seeing is the actual ground bond tester. And on the right side is our product under test, which is in this case a household fan. Connections 4 and 5 are the outputs and the sense connections for the high amperage, the ground bond current that's going to be injected into the ground pin. And if you follow that red lead all the way to the product's line cord, you'll see that at the point that's labeled 6, that's where it's connected to the ground pin on the line cord of the fan. The other connections 1 and 2 are providing the return path for that current. Obviously, when you inject some amount of current into a ground pin, you have to provide it a return path for that current to return and provide and then that way the ground bond tester can make the measurement. And the other side of that return clip is obviously, clipped onto the chassis or it could be a ground stud, chassis, any, exposed metal that may be grounded. You clip the return lead onto that, and the instrument starts outputting the high current, and in doing so, it makes the impedance measurement of the ground circuit. There's obviously a voltage drop, for a ground bond test. As we move on, we'll look at some of the requirements as per the test standards, and you'll see that they're specifying a current value, or giving us a way of calculating what kind of ground bond current we should use for our test or for our product, as well as it's giving us a pass-fail criteria of what's the maximum allowable impedance for a ground circuit for different types of products, as well as the test time and the test voltage, because in order to output some current, we do need some voltage, some force to push that current into the circuit. So keeping this picture in mind, let's look at what really goes on inside. So here's again, you can think of the same picture, but now we're looking at the schematic of the same picture. On the left side, we have our ground bond tester. On the right side, we have our product under test with a line cord that plugs into the ground bond tester. Usually, we recommend most of our products, ground bond testers come with a adapter box or a receptacle box to allow for a safe connection of the device under test to the ground bond tester. In some cases, like the previous picture we saw, we were showing just using test leads clips. That's also a way you can perform a ground bond test, but safety is our thing. So we want to make sure we give you all the tips on safely performing the ground bond test. So what happens here is, if you follow the green dashed line, you'll see that the high current is being injected into the ground pin, and it's measured back on the chassis of the product. So what really happens here is, we set the few of the ground bond test parameters that you want to set are the ground bond current, which is usually, in the amperes, 10, 20, 30, whatever that number is. Time, how long do you want to run the ground bond test? There are different requirements, per the standards, depending on whether it's a type test, design test, or a production line test. Timings may vary. Voltage at which you want to apply the current or inject the current, and the high and low limits for the resistance. That's what's going to determine whether the ground bond test is going to pass or fail. So in this case, what we're showing you is, current injects into the ground pin, makes its way around the chassis, and it's measured back on the chassis, and in doing so, it results in a pass. A fail condition for a ground bond test means that the measurement of the impedance of the ground circuit has exceeded the upper threshold that we have programmed in the ground bond tester. That basically means if you have a high limit of 100 milliohms, which is a very common number as per the test standards, if the test fails, what happens is the impedance measurement exceeds that 100 milliohm number, or 0.1 ohm number. And since the standards do not give us any leeway, or it's a strict 100 milliohm number that you have to meet, the tests, you cannot say that the test is a pass. So you'll have to go back and look at the ground circuit, see if there's a need for maybe offsetting any test lead resistance. Offset is also a feature available on most of our ground bond testers, so you could try that. And if even by offsetting you're still failing and you're still exceeding the upper threshold of the impedance of the ground circuit, you might want to go back and look at the ground circuit and see why is it high impedance. Maybe something's wrong, something's in there. It's not making a good contact internally. It could be a bunch of things that you might want to look at if you keep failing the ground bond test. But the first thing you want to do is make sure the connections are secure and you have offsetted any resistance caused by the test leads. Okay, so with that said, let's start looking at some of the numbers from the actual standards. What we've done here is that we've taken most of the common standards or test standards, by which I mean UL or IEC or EN, and we've basically summarized the requirements of those standards, the electrical safety test requirements that are applicable to our instruments and our type of test industry. And we've summarized those in our standards reference guide. So here's a little snippet from that. And what we're looking at right now is this IEC 60601-1 3rd edition, which is the big standard for medical electrical equipment. And this is a requirement for the ground bond test. As mentioned in the standard, sometimes it's called impedance and current carrying capability. It's the same name for a ground bond test. And this particular requirement is for a ground bond test during the design phase of the product. And if you look at the requirements, current is 25 amps or 1.5 times the highest rated current, whichever is greater. So that gives you a number to work with for the amperage. Pass-through protective earthing circuit, which is the ground circuit. Frequency could be 50 or 60 hertz, depending on what the product is meant for, where it's going to be used. And no load voltage of less than 6 volts. This is the voltage that I was talking about earlier, which is required to push that amperage through the ground circuit. So this is also a parameter that you need to account for when you're programming a ground bond test. And then for the pass criteria, impedance of protective earthing circuit on the DUT should be less than or equal to 100 milliohms. And then for DUTs or device under test with non-detachable supply cord impedance for impedances less than or equal to 200 milliohms. So here's our two numbers for our high limits for two different types of products. So if I'm testing a medical device per these specific requirements, I can program my ground bond output current for 25 amps, my no load voltage on my ground bond tester as 6 volts because it says less than or equal to 6, so 6 is acceptable. Frequency according to the region, and my high limit if I'm using a product with a detachable line cord, I'm going to set my high limit to 100 milliohms. And then if I'm using a product with non-detachable line cord, the standard is allowing me to have a high limit of less than 200 milliohms. And if you focus a little bit on this number, the 100 milliohm and the 200 milliohm, we're talking about a very small resistance, about 0.1 or 0.2 ohms. And the reason, again, for that is going back to the basics of, basic nature of current. That current always wants to take the path of the least resistance. So we want to make sure that the safety ground of our product is low enough resistance so that it never takes any other path but the path of the ground circuit. Another example from the standard, and this one is for LEDs or the luminaries industry, the UL 1598. And in this case, the ground bond, and then again, if you focus on the name, bonding circuit impedance, so all these, you'll see different names in the standards, which all are referring to a ground bond, what we know of as a ground bond test. And anytime you see a requirement of in the range of 10 plus amps, you can also tell that it's a ground bond test requirement. So 30 amps pass between earthing contact point and accessible conductive parts. So now here's another important point. If you focus on this, pass between earthing contact point and accessible conductive points. This means that there are products, whether it's medical or any other type of products, that can have multiple external grounding points, meaning that different parts of that product may be grounded. So that requires, in some cases, to perform a multi-point ground bond test, because you want to make sure you're checking you're checking the ground continuity and the ground bond, or the impedance of the ground circuit for different points from the main, from the ground pin of the line cord to A, B, C, or D, or however many different grounding points you have on your product. And again, that's also a possibility, and there's obviously ground bond testers and switching matrix available that allows you to perform a multi-point ground bond test to make sure all the different accessible conductive parts or points on the product are tested for continuity and ground bond. In this case, the no load voltage is less than or equal to 12 volts AC or DC. And then again, the ground bond test could be either AC or DC. And the test time in this case, it's giving you as a 60 to 120 seconds. So this obviously does sound like a design test, because normally a ground bond test for a production line is a 1 second test. And again, the impedance of protective earthing circuit on the DUT should be less than equal to 100 milliohms. So there goes your high limit. So the test standards, you'll see these numbers vary a little bit from standard to standard, but the basic concept remains the same. In the end, you are testing the same ground circuit of a product, of any given product, and the idea is the same. The purpose is the same. You're measuring the impedance of the ground circuit to make sure it's low enough and capable of carrying any fault currents. Another example from the 60335 standard provision for earthing tests. Again, a different term being used for the same test. If you look at the requirements, pretty much the same as the previous one. So anytime you see something along these lines, these kind of numbers, you can tell this is a ground bond test that the standard is talking about. And again, remember that earlier we saw class 1 and class 2 products. So the ground bond or the ground continuity test is not applicable for class 2 products because they do not incorporate a safety ground circuit. So then let's take a look at we did learn a little bit about what the ground continuity test is and what it's meant for. A purpose, is to make sure that a path is continuous. So now anytime you see the term ground with continuity, you got to remember that we're specifically talking about a ground continuity, like continuity of a ground circuit, because the continuity test also has different applications. Because you can test continuity between any part of a circuit or between any two given points. You can perform a continuity test and determine whether those 2 points are continuous. But a ground continuity test specifically means you're testing the ground circuit. The method for a ground continuity test is very similar to the ground bond test. A small pulse signal is applied and measured at the other end. And normally a ground continuity test is used as an add-on or a built-in test within the HiPod test. A HiPod test is something we've already learned in a bunch of different webinars. And right before performing a HiPod test, some HiPod testers incorporate a quick pass-fail for continuity, a quick continuity check built into the HiPod test as one of its, you could say, one of the HiPod test parameters, would be a quick continuity check. And that just gives us an idea whether the ground is continuous or not. And a lot of times it's just a visual indication, maybe a light, an LED on the tester might turn on. Specific to Associated Research products, you'll notice that if you've used a ground bond or a HiPod tester, from our brand, you'll see that if you do set the continuity function or the continuity check to on before a ground bond test, as soon as you make all your test lead connections, you will see that the green test button lights up. And basically that's indicating that there is ground continuity. It's measuring continuity. So the ground continuity testing is the same concept as a ground bond test. You're simply checking for a continuous path on a ground. However, there are key differences between these two tests. So before we get into more details about the ground bond test, let's look at a requirement for a ground continuity test. Because we've been in the previous examples from the standard, we looked at the examples of or requirements of a ground bond test. Now we're looking at continuity tests, and most commonly continuity tests are required as the end of production line tests, because a ground bond test is more commonly required as a type test. So you've already, when you're designing a product, you are required to perform a ground bond test for say 60 seconds or something, and the design of your product, if it meets the criteria and passes the requirements of the standard, you know that that's how the ground of all your products is going to be designed. So you don't really need to perform a ground bond test on once you move into production and start high volume production of your product, the design of which had already been approved by the agencies that you were working with. So if that happens, if that is the case, if you look at the test standards, most test standards do not require a ground bond test to be performed on end of line or end of production, or in other words, on fully assembled products, for the very fact that their design has already passed the ground bond test. So all you need to check is a quick continuity check and make sure that the ground is still continuous. Over the years, though, we have seen this change in trend where a lot of people in the different industries that are testing their products for a ground bond test during the design, they're also incorporating a ground bond test instead of a continuity test, for the very fact that the ground bond test is obviously a more stringent test. It gives us bit more information and a little bit more peace of mind that, hey, I designed my product, the ground has been designed according to the requirements of the standard, and now I'm mass producing my product, but I still want to make sure that the ground is still intact. So if you ask me, I would be more leaning towards running a 1-second ground bond test on fully assembled products, and that's what we have seen over the years. And if you look at this requirement from the 61010 standards for test and measurement equipment, a continuity test to be run on the protective earth circuit, no current value specified, simple continuity test to show existence of protective earth circuit. So this is a very, very basic requirement. I could just take a basic continuity, digital meter, a handheld meter, and check for continuity. So the requirement is not that strict. It's not giving you any numbers, anything else, any parameters. It's just telling you to make sure the path is continuous. But that's still, as we look at some of the next slides, you learn that, the key differences between a ground bond test and a ground continuity test, they lead us to lean more towards running a ground bond test, even on fully assembled products. A 1-second ground bond test, for example. Some other examples from standards. This one is, now in this case, if you notice, the 60335 standard is actually asking for a ground bond test as a routine test, or a end of production, test, production line test. So in this case, a ground bond test is required on fully assembled products, 10 amps and 12 volts, less than equal to 12 volts, impedance of the circuit, less than 200 milliohms, and for other appliances, less than 100 milliohms. But the key difference in this requirement is that this is a routine test. The previous ground bond test requirements that we looked at were for the design or type test. This is a routine test requirement, which is a little not very common, because ground bond test is normally not required as a routine test by most standards, but the 60335 does require it. So you have to perform a ground bond test on your fully assembled products. So let's start talking a little bit about the differences between a ground bond and a ground continuity test. So and we may have already covered most of these, but it's always good to kind of review and summarize the key differences. So on the left side, ground continuity test verifies the existence of a ground circuit. Okay, all it's telling us is that there is a continuous circuit. It won't tell us whether that ground is, how good that ground is, and how much current it can handle. Whereas on the other hand, the ground bond test verifies the integrity of a ground connection. So that's a more stringent test. Readings are normally given in ohms for the ground continuity test and in milliohms for the ground bond test. And again, looking at one of the requirements we just saw for the ground continuity test, there are no pass-fail criteria other than the fact that there is continuity. The ground continuity test is quick to set up and easy to perform. The ground bond test is also pretty much the same type of setup. It's just that the output, is a higher current, so you have to be more careful and make sure it's being performed in a safe way. And the ground bond test provides a more valuable safety information about the device under test. Obviously, when you're applying a higher current, higher amperage to a ground circuit, it basically gives you a value of impedance of the ground circuit. Again, usually for the ground continuity test, it's usually used as an extra feature during the HiPod test, which we already talked about. And for ground bond test is a test of its own, so it's not built into the HiPod test. It needs to be performed most commonly before a HiPod test, because before you test the insulation, you want to make sure that the ground is intact and in good condition. And again, in the end, the ground bond test is more stringent than the ground continuity test. Hence, we've seen this change in trend over the years where different industries have adopted to performing or running a ground bond test on production units. So a little bit more about the differences between the ground bond and the ground continuity test. And in this picture, what you're looking at is a wire, a big cable with bunch of different small wires, which are basically inside the insulation. And in this case, we're showing a 64-strand wire with all but one strand connected. So in this case, if we were to run a ground continuity test from the left side to the right side, we will see a pass because there is at least one strand connected, and it will give us an indication that there is continuity, and we will pass the test. But what this won't tell us is that how good that one strand is, how much current can it handle before it melts or heats up too much. So 64-strand wire with all but one strand connected. A ground continuity test would pass this wire because the instrument reads a continuous path. Now, if you were to run a ground bond test with only one strand connected, this is what's going to happen. The strand will most likely, the one wire will most likely melt because it will not be able to withstand the higher current, the higher amperage passing through it for a given amount of time. Whereas if this cable was, so in this case, a ground bond test will result in a fail, and it'll give us a good indication. So now think about this in terms of your product's ground. In case on your fully assembled products, that you've already passed the design criteria for the ground bond test. But what if there's an operator error or machine error and the ground is not being installed properly, or is just barely making contact with the chassis at some points? A continuity test will not tell you if there's a problem with the ground, but a ground bond test will definitely catch these little things, which can result in big issues later on. So that's the reason why we've seen the change in the trend where a ground bond test is being used on fully assembled products on the production line. So in this case, a ground bond test load the wire with high current. This would burn up the connection and cause a fail. So this is the reason why a ground bond test is considered as a more stringent test, and the reason why industries are adopting to performing a ground bond test on fully assembled products. So that leads us to our first poll, or the only poll question for today. When are you performing the ground bond test on your product? So please take a moment to answer this, and we'll pause there for a second.
Hey Syed, we had 33% say during the design phase and 67% said during design and production.
All right, thank you, Brittany. Okay, again, thank you for participating in this poll, and it looks like we have most of the people are running a ground bond test as expected during design and production. So it looks like you guys are already adopting to performing a ground bond test, as a design test, as well as on fully assembled products. There's a few, 33% who said, or who noted that they're running a ground bond test during the design phase only, which is also obviously, you're complying with the standard, so nothing wrong there. But the interesting number is the 67% selecting the second option, which is what we had expected. So the next thing, I think we're reaching toward the end of our webinar. The next thing what I'm going to do is play a quick video of a ground bond test. And in that video, what we'll do is, what we're showing is a ground bond test being performed on one of our test verification boxes. It's a pass-fail test, but what I want you guys to focus on are the results of the ground bond test. So bear with me 1 second here. So before I play this video, the first test is a continuity test that we're going to show. Just a simple continuity pass-fail check. And we're going to clip the leads onto the ground bond, on the ground bond pass and fail. So we're going to start with a ground bond pass test. So here, let me take it back a little. All right, here's where I want to pause, because this is what's showing us the results of a ground bond test that's being performed in this video. So if you look at the current 30 amps, okay, and that's basically the current that was applied to this path, and the resistance measurement comes out to be 62 milliohms. And again, the reason we're passing this test in this case is because our high limit was probably set to 100 milliohms, which it did not exceed, so it results in a pass. And then we're going to do a quick ground bond fail check. Okay, so I gotta go back a little and make sure you guys can see these numbers. Okay. Hopefully I've paused it at the right time. So in this case, we're applying the same 30 amps of current into the test path. And if you notice at the bottom, the resistance says greater than 200 milliohms. So obviously in this case, we're failing the test because we're exceeding the upper threshold that we have programmed in this ground bond test. So basically, those are the type of results that you see in a ground bond test. And here, let's take a look at all the tests that were shown in this video. The first continuity pass test resulted in a 0.63 ohms. And then the other one was a continuity high limit, which is 2.13 ohms, exceeded the high limit. Ground bond pass and ground bond fail. So before we end the webinar, one more thing I want to mention here, when you're performing, and I want to go back real quick to one of our circuits for the ground bond test. And, just going a little bit more in detail on how the test is actually performed and how the current or how the resistance is measured. When so first of all, when you're applying, a certain amperage at a given voltage, say 6 volts or 8 volts, what happens is when that current makes its way through the ground circuit and is measured back on the chassis, there's a voltage drop that occurs in, as a result of that current flowing through that resistance, because, it's going to seed resistance, and, that's going to result in a very small voltage drop, which is usually in the millivolts or a very, very small value. The ground bond tester takes that voltage drop and uses the Ohm's law to calculate the resistance. Resistance is equal to voltage divided by current. So it takes we know the voltage that we're applying. Okay, I mean the voltage drop that we see of in the millivolt range, and we know what kind of current we're applying. In this case, 30 amps of current. So if you do the math, you're dividing a very small number, a millivolt number, by 30 or 20 amps, and the resulting resistance measurement is in the milliohms, and that's the reason why we measure such a small value, because that voltage drop is what's basically helping us calculate the resistance. So that's how the ground bond test theory works. Basically, it's all about how much voltage drop occurs when that current flows through the path. So that leads us to the end of our webinar today. But before you guys leave, I'm gonna have some time open for any questions that you might have posted on the chat line, and if there's anything that Tony wants to bring up here, and I can talk about those. Anything that you want me to cover again, any questions on the material, this is the time to put those up on the chat line.
Looks like all the questions were answered during the webinar, so we're good.
Okay, thanks, Tony. Okay, well, it looks like there are no questions, or all the questions have been answered by Tony on the chat line. I do want to mention before we sign off today that to visit our website, arisafety.com. We have a big library of white papers. All these webinars are recorded and posted. You can view them if you've missed any of the previous webinars of 2018. And our next webinar is on September 12th. This is a new one. This is the first time for us as well. What we're doing is we're changing the topic a little bit. We're moving away from electrical safety in terms of like the high pod and the ground bond tests and etc. We're going to talk about power, strictly power, and related to power sources. So do join us on September 12th, 10 a.m. Central Standard Time, US, and click the link in the chat box to learn more. We also have our applications consulting program, so do visit us on our website to learn more about our consulting services, or contact us, and we'll be happy to explain you what that's all about. If you want a copy or a recording of this webinar, you can go on our website and the webinar page given in the link on the screen, and our main website. And also, any questions, please email to Brittany. And I do want to announce that this is the last webinar that Brittany is going to organize for us. She's moving, she's moving up a role, and we'll have somebody else replace Brittany for the next webinar. So I want to thank Brittany for all her hard work that she's put in over the years to help us successfully run this webinar show. So thank you, Brittany, and you will be missed. And with that said, thank you everyone for joining us today and taking out time to be with us. And we hope to see you next time. This is your host, this is your presenter, Syed, signing off from Lake Forest, Illinois. Thank you.